Hello everyone, welcome back. I hope you enjoy your holiday, and also I hope you still remember what we learned before. So this is our last lab for Lab 9, and we will add PC in our CPU. So after this lab, your CPU is ready to use, so you can post a new status on your Facebook page and say, everyone to look at or check out my new CPU. Yeah, that's cool. Okay, let's go to start our lab. So first, let's go to our website and open the PDF file. So here is the CPU we have for from the Lab 5 to Lab 8, and we already support I-type, R-type instructions and also have data memory. But for this week, we want the CPU to run it automatically. So here is the previous CPU and this instruction. Originally, we gave the instructions in the test bench, but we want to save the instructions in another memory. It's called instruction memory, and use another register called programming counter PC to read automatically from the instruction memory. And whenever the PC gives it the values go from the PC goes into the instruction memory, and the PC increased by 2, we'll move to the next address to run. So this is how the CPU can run it by itself. But pay attention to here. Since we have 16-bit CPU, so that's why the PC plus 2. And for your MIPS CPU you learned from the lecture, that's different. So this plus 4 in your lecture. So pay attention, that's different. Okay, let's see how to do that. So open your project, and here are the signals we need for this lab. Actually, there are 3 new signals we need for the PC part. The first part is instruction fetch. Originally, we break down the instruction to 4 parts, but before that, right now the instruction is not a port, it's an inner signal right now, and it's read from the instruction memory. So we instantiate another memory, it's called instruction memory, and here is the PC register. In the PC register, the input of PC register is PC plus 2 underscore 2. So this is a signal here. And the output port is PC register output. So whenever you have the value, the output plus 2 and it goes back into the PC. So the PC will increase by 2 automatically. And the output, the PC register out, is the address goes into the instruction memory. Since this memory is read-only, so the only read enable is 1, but write enable is always 0. And since this read-only, so we don't have to write into the memory, so the input data is always equal to 0. And the output of this memory is instruction we will use. So that's it. After I change the top module like this, so the CPU can run it by itself. And for this case, the test bench, you don't have to modify any test bench because the test bench have nothing in it. For this case, we have to save our instructions in the instruction memory, which means we have to initialize the instruction memory. All the instruction you need to test is here. So here's a list of the instruction you need to test. And we have to convert it from instruction to the binary code, right, which is machine code. So if you still remember, at the beginning of the class, I said we need a compiler to compile the assembly code to the machine code. So you can click the compiler and open it. So this compiler is written by one of my students 2 years ago. He created this website and specific for our class. You can write assembly code on the left. Okay, and the machine code is automatically generated on the right window. So I type in all the instructions you need to test here. And on the right side is our instruction initialization files. Okay, press Control A to choose all of them and copy the data. So where we should put it? Okay, let's go to our projects. So in this project folder, you can find a file named instruction.txt. Double click to open it. You can see this file is empty. So paste all the initialization file here. Okay, pay attention. Don't add one more line here. Okay, just leave it as that. Okay. Don't add more. Okay, so you can move the top to see there's some values here. Okay, and don't leave any white space or empty line before this. Okay, just keep like this. Save it. Save the file. Okay, and then you can simulate it. Okay. Okay, let me show you the simulation results. So if you run it correctly, the simulation is like this. So I just skipped the process to drag the signals, but I have to show it to you because after you simulate it, there's nothing in the wave window. Please listen carefully. So first we need to add instruction. Instruction is inner signal. So on the left window, click UUT, and on the right object name, you can find the instruction. And right click, add it to the window. Okay, add it to wave window, and change it to the hexadecimal number. The register file on the left here is register, and the last signal register file. Drag it or add it to the wave window. And one more is the memory. The memory is in the memory parts on the left, and click the memory signal and right click and add to window. Okay, so if you follow our previous video recap, you quite know how to do it. And both the register and the memory, change it to the decimal signed decimal number. Okay, if your instruction.txt file is correct, you can see the simulation results have the certain values for instruction. By the way, change the simulation time to 1.5 ms and change this value and restart and simulate again. So if you follow our video recap, you know how to do that. Come on guys, this is our last video recap, so you know how to do it. I believe in you. Okay, so that's all the results. You can compare the results with my window here and to test with your window. So that's the correct results, and also for the memory. To say have a screenshot, have the wave, but don't forget to keep the register and the memory to show everything here. Give it a screenshot and save the values in this table, and as the second. This is the second screenshot, and in your lab reports as usual. Okay, so that's the requirements for Lab 9 is our last lab. Okay, thank you for everyone to join our class, and I hope you'll learn something through this semester, and good luck for your finals. Thank you. See you next time.